Okay, here we go. We are going to go over 5.1 and meteorology notes 5.1, which is on the greenhouse effect, which we didn't completely finish up before you left class today. And we're also going to go under notes 5.3 and 5.4, which are weather variables. And we're going to talk all about that stuff tomorrow in class and on Wednesday in class, but you got to make sure that you get down the notes today and listening in today. So really quickly, first and foremost is the greenhouse effect. So we have, in the greenhouse effect happens every single day, and we like it because it warms up the planet. And what happens regardless of whether people are here or people weren't here. So we have ultraviolet radiation, UV, and visible light. High energy coming in from the sun. The squiggles are high frequency, high energy. They hit the earth, it's absorbed and it's re-radiated. Okay? There are three gases in our atmosphere that do the principal amount of absorbing of infrared radiation. We have water vapor, H2O with a little v, water vapor, and we talked about that today. We also have CO2, carbon dioxide. And methane, which comes from CH4. Okay, we covered that. What we didn't get to today in class is where they come from. If you don't know where water vapor comes from, then that makes me sad. But it's pretty much from the oceans on the earth, okay, and other bodies of water, mostly the oceans. Okay, so that's easy. And water vapor can range a ton. Okay, it can be absolutely nothing in the atmosphere or a very, very small amount in some deserts in South America and in Australia and Africa, or in Antarctica. Believe it or not, Antarctica is a desert, even though it's surrounded by ice. It's still really cold, so there's very little water vapor in the atmosphere. Or carbon dioxide comes from burning of fossil fuels, okay? Fossil fuels, okay? No, fossil fuels. And burning things, okay? Driving around, cars, industry, all that jazz, okay? Methane. Methane is something a little bit, okay, so it comes from multiple places, okay? First and foremost, it comes from livestock. Pigs, cows, animals that eat grasses have acids in their belly that give them methane that comes out the fanny, okay? Without all intent and purposes, there you go. Livestock produces a large quantity of methane, typically cows and pigs. Another one, you're driving down Quaker Road, out near Alpco, there is a field of candy canes. That candy cane is basically an old landfill, okay? So garbage gives off methane. The decomposition of matter gives off methane. The reason why those candy canes are in the field, they're pipes that allow the methane to come out of the ground. Okay? So these two principal sources are where the methane comes from. Okay? CH4. In terms of amounts in the atmosphere, water vapor is the most, carbon dioxide is a smaller amount of the greenhouse gases, and methane is the least. Methane is the most powerful. Okay? Carbon dioxide is a little bit less powerful, but there's more of it, and water vapor is a little less powerful, but there's even more of it. So that kind of teeter-totters back and forth. Most amount, least powerful, in between, most powerful but least amount. Boom, there we go. That's what we got for the greenhouse effect, okay? I'm going to shut that one down. Come on. No, I don't want Smart Notebook to open. We're going to edit this out of the video. Okay, on to notes. Okay, on to notes. So, weather variables. Okay, there are 5 weather variables. First and foremost is the most obvious, temperature. Temperature changes every day. Okay, I'm going to start sounding like a meteorologist at the beginning of class. We have 5 weather variables and they change every day. They're going to be logged and categorized and listed in what's called a weather station. We're going to learn about that later on this week. Okay, but temperature is the most dependent upon or changeable one that we can recognize. Okay, and we measure temperature with a thermometer. You need to know the instruments that that record and measure weather variables. Temperature is easy, it's a thermometer, okay? You need to know how temperature changes with regards to seasonal changes. That's what we talked about with Earth and space, and now we're moving into meteorology. Basically, summertime towards the sun, more duration of insolation, more or higher angle of insolation, so that means that it's going to be warmer, okay? Farther, December, even though we're closer to the sun, we get less amount of daylight, lower angle, it's colder. So that's going on with temperature. We're also going to take a look at what happens with regards to latitude. Is close to the equator, sun's high overhead, lots of energy from the sun, lots of direct insolation, incoming solar radiation. That means that it's going to get hot or be hot. As I move away from the equator, it's going to get colder. This stuff should be pretty basic. You should recognize and understand that. There shouldn't be anything exciting or oh my goodness about it. Okay, we are going to do a couple labs on it that you guys will graph on the computer. It's pretty straightforward. Okay, altitude and temperature, another pretty obvious one. As I move up in the atmosphere, there's less atmosphere to convey that temperature, so that it means it's going to get colder. Okay, so as I increase my altitude, temperature drops. So that's an inverse relationship. Okay, so continuing. Okay, so the first weather variable that you haven't really probably talked too much in middle school about is humidity. Okay, there's two types of humidity. We have relative and absolute. Absolute humidity, if we have time, we'll figure out in the room, we'll calculate how much water vapor is actually in the room. Okay, utilizing a few instruments, and that's a fairly easy representation. But more per se, we're going to take our time to study what's called relative humidity. Relative humidity is what typically people express when we're listening to weather reports and what's on weather station data. Why? Because relative humidity is easily accessible, it's easy to measure, and it's not, an absolute humidity is actually measuring how much water vapor is in the air, and that's not what we want. We just want a relative percentage. Okay, so when we obtain relative humidity, we use a psychrometer, not a psychometer, a psychrometer. Psychrometer is two thermometers together. Here's one, and here's two, taped together. Okay, one has a wet cloth on the end, a little water's dabbed on it. Okay, I'm going to step off screen. I'm going to put a little water on the end. Now the water is not to cool the thermometer down. That's not its purpose. Okay, the water is to measure evaporation. Okay, if the air is really dry, then the water in the little cloth at the end of this thermometer is going to evaporate really quickly. And when evaporation happens quickly, that cools things down. Okay, so that's going to make the one side of the thermometer change as I expose it to more wind or more surface area. The wind blowing over that is going to create more evaporation. On the other side, I have a thermometer that has no little water cloth attached to it. And because of that, it's going to stay dry. So what we label this, or what we term this as the wet bulb and the dry bulb. So I'm going to spin this around while I'm doing the rest of the notes. Okay? So when we're talking about relative humidity, again, relative humidity, we're going to measure the dry bulb temperature versus the wet bulb temperature. Now, some of you may be thinking, oh, Mr. Perry, as I'm spinning this around, there's a centrifugal force and there's some physics pulling down on this. Now, because it's such a small tube, the alcohol in the thermometer, not mercury, mercury thermometers are long gone, the alcohol in the thermometer isn't really affected. Plus, even if it was, they're both being affected equally by the centrifugal force of me spinning this around. So it's really a non-issue, okay? So after I'm done spinning this around, okay, I'm going to have two temperatures. On one side, I have the room temperature, the dry bulb temperature, and it's 74 degrees in here. No biggie. And on the other side, I look and I read the thermometer temperature being 62. So on one side, I have a temperature of 74. Must have been all you hot breathing bodies in here before. And I have a temperature of 62 on the other side. So there's a big difference, a big change between the warmth of the air, dry bulb, and the evaporation or the cooled by the little cloth at the bottom here, and it's changed that temperature. Now, we're going to use some charts in the reference tables to calculate what the relative humidity is, but we can also figure out not only the relative humidity, but what's called the dew point. The dew point is not when I pick up my 2 liter and go for that. Well, it is a very good opportunity to grab for the dew point. The dew point is specifically when we have atmosphere or the water vapor in the atmosphere that gets cool enough where the water begins to condense. It reaches 100% humidity, and that's when you get a cloud. Not the dew point here. So, continuing. We have the atmosphere's ability to hold moisture is the relative humidity, okay? When the atmosphere is warmer, it holds a lot more moisture. Okay, the air molecules spread out, water vapor molecules can get in there, mix it up, happiness, okay? Whereas when it gets cooler, they condense together, and it sort of doesn't allow the water vapor to evaporate as readily into the atmosphere, okay? So, there we go. Relative humidity is what we talk about. Specifically when it's sticky. Think about when you notice the relative humidity or when you notice humidity. Typically, it's in the summertime when the air is warm and it's muggy and it's hot and you can't sleep at night. Why? Because of the fact that that's when it's warmer, and that's why it holds more water vapor. And that way your sweat doesn't readily evaporate. Okay, just like the wet bulb temperature, if it's warm and it's wet, the moisture won't evaporate from the thermometer. Whereas if it is, or the cloth on the thermometer, whereas if it was a situation where it evaporated really quickly, like right now I'm warm but the air is dry, so I get evaporation that readily occurs. Of course, I also get dry skin. That's the reason in the wintertime you have dry skin, because there's so much evaporation it begins to steal it from your skin, and that doesn't. Some people's skin don't like that very much, or it steals it from your nasal passages and your bloody nose. So, anyhow, the relationship between humidity and temperature is a direct one. Okay, so that's relative humidity. That's temperature. Those are the first 2 variables we've talked about. Now let's talk about the other ones. Okay, that would be pressure. Pressure is the hardest one to understand. It's the one that we're going to work on the most because of the fact that pressure is something that, unless you're at the bottom of the pool, you're really not feeling. Okay? Wait a second, Mr. Perry, you're talking atmosphere and you're at the bottom. Well, pressure on your head is when the water's squeezing on you, and that's pressure on your head too. So, we talked about relative humidity and temperature. The other component of weather variables that are connected directly to humidity is the air transparency. Transparency is the ability to see through something. So if I can see through the air, and it's clear, it's clean, there's not a lot of moisture in it. If I can't see through the air, fog, rain, pick your favorite form of precipitation. Buffalo 2 weeks ago had tremendous amounts of snow. They couldn't see it all. Why? Because there's a lot of water vapor in the atmosphere. Okay? So air transparency. There's 3 types of air transparency we measure. We measure visibility, the ability to see horizontally along the sky. Okay? We also measure cloud cover. Cloud cover is an easy one. Look up in the sky, it's either 100% cloudy, quarter cloudy, 3/4 cloudy, partly sunny, whatever. And last but not least, we have the cloud ceiling. And that's the level at which the clouds formed. Today we saw a picture where there was hats on top of mountains. Okay? That is the cloud ceiling. It's where the clouds begin to form. Okay? All dependent upon the relative humidity. Okay? Visibility, again, is the horizontal distance. Okay? We have cloud ceiling is the vertical distance I can see, and cloud cover is just the fraction of the sky that's clouded over. But the big one is pressure. Okay, that's the one that I'm really glad, hopefully you're watching this video and getting down. Okay, so pressure, okay, and it's not just a song sung by Billy Joel. It's that feeling you can feel at the bottom of the pool. It's the feeling when you're driving on State Road 14 going down into Geneva, or you're going down on 96 into Ithaca. When you come off of those hills into Geneva or Ithaca, you got to yawn. You got to pressurize the eardrums, okay, or depressurize them, because you're changing your elevation, okay? That's air pressure. Really don't deal with it very much, but it's there, okay? We measure air pressure with a barometer. It's as simple as that. Barometer is, you can have a spring barometer or a mercury barometer, which you wouldn't see in school. But again, it's something, the air compression of the spring and we can measure air pressure. Okay, air pressure and temperature are very, very important, and you have to understand this relationship in earth science. You have to understand it. They are opposites. They are inverse. When the pressure is high, temperature is low. That's why on a weather map, the H's are blue, because we relate blue to being a cold temperature. When the temperature is warm, temperature's warm, okay, then the air pressure is low. Okay, that's why the L's are red, because the warm air rises, okay? So, or the cool air really pushes the warm air out of the way. Depends upon the way you look at it. But anyhow, when air rises, it creates an area of low pressure. Okay, when temperature goes up, the air pressure goes down. Opposites. So it's an inverse relationship between temperature and pressure. Okay, really, really important, okay? And you're going to need to know it, and I can guarantee you on like one of the first 20 questions of the test in June, you're going to see something on the way low pressure moves, okay? And the way pressure is related to temperature. Okay, so on your note packet, this isn't filled in. So this is a way I'm going to measure whether you actually watched this video or not, or ran around and scrambled and copied from somebody else. But, okay, you need to fill this in. Okay, so low pressure, we have a side view and we have a downward looking view, an airplane view. So the side view, we have air converging and rising and creating a nice poofy cloud. Whereas high pressure, the air is descending. Notice no cloud, with this Mr. Golden Sun shining. Okay, so it's clear and cold, and the air is diverging, spreading out. Whereas on low pressure, it's converging and rising. Okay, make sure you copy that in. Only the H's and L's are on your note sheet. Okay, low pressure, counterclockwise and inward. Okay, counterclockwise and inward towards the center. Okay, whereas high pressure is clockwise and outward. So we have spreading out and circulating around. Low pressure is counterclockwise and sucking the air in. It's not really how low pressure works, but for earth science, what you need to know, this is where it's at. Okay, if you take a class of meteorology this week or someplace else, there's a little more of a detailed relationship in how winds break because of the Coriolis effect. But suffice to say, in this class, this diagram works, that diagram works, this diagram works, and this diagram works. And you got to know it. I'm going to back up. You take a still on this and get it down. Okay? Okay. Last but not least, before we move on, all pressure systems move from the United States west to east. Okay? All pressure systems move from west to east. You will constantly have that question. You got to know. Everything moves from west to east, unless there's a nor'easter, but we'll talk about that too. Okay. Last but not least, air movement. Air movement is simply the wind speed. Okay? And air currents. Either the air can be moving up and down, or the air can be moving around across the ground. Across the ground, it's called wind. Up and down, it's called an air current. Okay? Okay. We measure wind speed by what's called an anemometer. Anemometer. Okay, an anemometer. Okay, A with omometer usually gets you the credit. Just make sure you know it's an anemometer. Also, a windsock can measure wind direction or a wind vane, but for the most part, it's anemometer that measures wind speed. Okay, so usually, the greater the difference in pressures, we have a direct relationship. So the greater the difference in pressure, the greater the wind speed. And that's basically it for our 5 weather variables. 5 weather variables, okay? We covered 2 in the previous note sheet, 3 in this one, and now we're set. Thank you very much for watching the video, and I look forward to talking to you guys tomorrow in class.